Yeah, hello everyone. Today's lecture will be devoted to Gauss law. It will be the last lecture devoted to Gauss law, although tutorial on Wednesday will be related, actually entirely devoted to Gauss law. And you can expect, of course, questions on test number 1, questions related to Gauss law as well. So I hope you can hear me. Could somebody?
Yes, we can, sir.
Yeah, thank you very much. Yeah, so last time on Friday, I at the end of the lecture, I was explaining how to use Gauss law to calculate electric field produced by a sphere of charge. So, so I want to repeat this solution again because I did it quite quickly and at the end of the lecture on Friday. So on the screen, you see the Gauss law. But by now, hopefully, you all remember what is the mathematical form of Gauss law, that the flux of the electric field through a closed surface must be equal to the charge, the net charge inside of that surface divided by permittivity constant. So this is the equation, which means that the left-hand side must be equal to the right-hand side, of course. And no matter what is the shape of the surface, of that closed surface, no matter what shape you select, that the flux of electric field will be the same and must be equal to that net charge inside divided by epsilon naught. When I say charge, net charge inside, remember that might be some positive, some negative charges. You have to calculate the net charge inside of the surface. So our purpose, however, is to calculate electric field produced by these charges located inside of the surface. And as you see, electric field is here under the integral. So what we have to do, we have to select always a surface, that closed surface of a simple shape, so that it is easy to calculate the flux of electric field. Because for complicated surfaces, of course, the magnitude of electric field over the surface can change, direction can change, so that surface integral can be, in general, very complicated to calculate. So what we did was this. We had the sphere of charge, let's say plastic, piece of plastic, spherical in shape, with the positive charge embedded in it. And the charge distribution is uniform. So the volume charge distribution is uniform. And we want to calculate electric field, let's say at certain location, a distance r from the center of the spherical charge. Let's say at this point, somewhere at this point, a distance r from the center of the spherical charge. So to calculate electric field, we should select, and to use Gauss law, we select the closed surface, which we call Gaussian surface, which passes through that point where we want to calculate electric field. And the most convenient surface here is spherical surface. So here, surrounding that volume of charge is the spherical surface. You see just cross-section of that sphere. So you see a circle, but it's a three-dimensional surface. And every point on that surface is the same distance from the center of the sphere, right? The same distance from the center of the sphere. And for that reason, we expect that electric field, magnitude of electric field here, on any point on that surface is of the same magnitude. Of course, directions are different. We expect that the electric field produced by the spherical charge is radially away from the center. So here electric field at this point would be radially in this direction. At this point, it would be radially in this direction or in this direction. But magnitude of the electric field should be the same on that surface. So let us evaluate then the flux of electric field through that spherical surface, which is given by this integral. The dot product, E dot dA, will be E dA cosine 0, because as you see, that area vector dA is perpendicular to the surface, which means it must be parallel to that radial direction at that point on the surface, right? So the area vector is perpendicular to the surface, and parallel to electric field. At every point on that surface, that is correct. So the dot product will give me EdA cosine 0, because electric field on the surface of the sphere is the same. So I can take E and cosine 0 in front of the integral, and then I have to evaluate integral dA, because now integral dA is the total area of the surface, which is 4 pi r squared. Right, surface area of the sphere is 4 pi r squared. So yeah, so the flux now must be equal to the charge inside divided by epsilon naught. That's what I have written based on the Gauss law. And from this equation, we find electric field. Divide by 4 pi r squared, and that would be electric field, a distance r from that sphere of charge. So this is the expression how to calculate electric field due to any spherically distributed charge. And so the same, of course, expression we used previously when the charge was a point charge, not a spherical charge, but point charge. So as you see, if the charge is spherical, then from the point of view of calculation of electric field, we could treat that volume of charge as if it is located at the center of the sphere, as all the charge is at the center of the sphere, because the point charge located at the center of the sphere would give the same electric field. So this is the proof that the Coulomb's law is valid either for point charges or spherical charges. So that much was done last time on Friday. Any questions before I continue? So that was a review of the Friday's lecture.
Professor?
Yes?
Would this equation be applicable with any scenario with a spherical surface?
Yes.
Or is it only when lowercase r is greater than uppercase r?
Yeah, so this is a good question that, no matter what type of size of the sphere of the charge is, the capital R is the radius of the spherical charge. So as long as that charge is inside or like here, then this equation will be valid. But in addition, maybe this is not your question, but even if that volume of charge here would be replaced by a spherical shell of charge. So imagine that I have a spherical shell. By shell, I mean, it's like now, like eggshell, right? Very thin, let's say, shell, but spherical shell. If the charge would be only in that spherical shell, as long as that shell has spherical symmetry, then the charge outside of that charge would be still given by this expression. So any type of spherical charge distribution would give me that equation, whether it's volume of charge or spherical shell, that would give the same result, because the total charge inside would be the total charge on that shell, right?
Thank you.
But yeah, okay. Additional questions? I am not sure if that was your question, but if not, you can maybe reformulate your question.
No, you answered it, sir. Thank you.
Yeah, thank you. So that's good. So let us do now the next part of this question. The second part of the question is slightly more complicated, which I did not do on Friday last week. So now let us try to calculate electric field at certain point inside of that spherical sphere of charge. So here we have that spherical charge of radius capital R, but I now want to calculate electric field a distance lowercase r, but inside of that sphere of charge. Let's say at this point, what is the electric field inside of that spherical charge? Distance r. So this time lowercase r is smaller than capital R, and I want to calculate that electric field at this point. So again, because of that spherical distribution of charge, right, and uniform distribution of charge and spherical distribution of charge, we expect that if I take the Gaussian surface, again, passing through that point where I want to calculate electric field. So if this is my spherical Gaussian surface, then at any point on that Gaussian surface, I expect that electric field has the same magnitude, because every point on the surface would be the same distance from from the center, and that would be reasonable expectation that the electric field should now be the same in terms of magnitude at every point on the sphere. In terms of direction, again, I expect that direction of electric field at any point on the sphere is radially away from the center of the sphere, because that would be the only reasonable direction for that spherical charge distribution. So at any point on the sphere, electric field is radially away, but the magnitude of the field on the sphere is constant. So again, I have to use Gauss law, and evaluate the flux of the electric field. So here's the same calculation, that any little area of that spherical Gaussian surface I take, vector dA would be parallel to electric field. Little vector dA would be parallel to electric field, because area vector is perpendicular to the surface, which must be along the radial direction. So again, I would have EdA cosine 0. That dot product would give me EdA cosine 0. E, electric field is constant on the sphere, so I would take E cosine 0. Cosine 0 is 1, of course, in front of the integral, and then I would integrate over this Gaussian surface, which would give me, again, the area would be pi r squared. So now here I see that I don't know why I have written twice electric field, which is obvious mistake. So I delete that one E. So yeah, so the flux would be E times 4 pi r squared, and that flux must be equal charge inside divided by epsilon naught by Gauss law. But the problem is now that Q inside is only charge inside of that Gaussian surface. So I have to calculate how much charge is inside of my Gaussian surface. You see, not all the charge on the sphere is inside of the Gaussian surface. So to calculate how much charge is inside of the Gaussian surface, I can use the fact that the volume charge density is uniform in that sphere of charge, uniform. And the volume charge density, which we used to designate by letter rho, is amount of charge divided by the volume. So the volume charge density for the entire spherical charge must be equal the total charge in that sphere divided by total volume of the sphere. Just in case if somebody does not remember the formula for the volume of the sphere, it is 4/3 pi r cubed. Capital R is the radius of entire sphere of charge. So the total charge by total volume, that's the volume charge density. But the same volume charge density must be applicable to that volume of charge in the Gaussian surface, which would be charge inside of the Gaussian surface divided by the volume of Gaussian surface. And Gaussian surface has radius lowercase r, so 4 pi r cubed. So from this proportion, then, I can find what is charge inside. Of course, 4/3 will cancel, pi will cancel, and then you get that charge inside is equal r lowercase r cubed divided by capital R cubed times q, right? So only that fraction, lowercase r cubed divided by capital R cubed, that fraction of the total charge q is inside of the sphere. Right? So from that proportion, I did calculate how much charge is inside of my Gaussian surface. And now that amount of charge I have to substitute here, you see, for the Gauss law. So I evaluated previously the flux, which was E 4 pi r cubed, r squared, and that flux must be equal charge inside divided by epsilon naught. Okay, so that's the equation from which I can find the electric field. So electric field would be equal now Q times, I made mistake here, like Q. Yeah, so first of all, yeah, I did not make mistake. So that r cubed and this r squared, I simplified. So only one lowercase r is remaining. So it would be lowercase r times q divided by 4 pi epsilon naught r capital R cubed. So this is the result for the electric field inside of the cube. inside of the spherical shell of charge, spherical sphere of charge, I should say. So as you see, the electric field depends on the distance lowercase r. You see, lowercase r is a numerator. An electric field depends in a linear fashion with respect to lowercase r, because capital Q, capital R, epsilon naught, these are constants. So you see, so that electric field depends linearly as a function of r. This is the plot, that if you plot the electric field as a function of lowercase r, then the electric field increases in a linear fashion. Once you get to the surface of the sphere, when lowercase r is equal to capital R, then the electric field changes as 1 over r squared, which we showed on the previous slide. On the previous slide, remember, we took when r was larger than lowercase r, and outside of that entire charge, electric field depends as, remember, as q divided by r squared, right? So this is the dependence, 1 over r squared. But inside of the sphere, electric field increases in a linear fashion from 0 to that maximum value, which is equal now q divided by 4 pi epsilon naught r squared. Because when lowercase r is equal to capital R, then of course capital R and r cubed would reduce to r squared, right? Because if r is equal to capital R, then r and r squared you could reduce a little bit. So the maximum field is equal q divided by 4 pi epsilon naught r squared. So that's how we calculated electric field inside of that volume of charge. So I'm sure that you have now many questions. So I will clean the screen and wait for your questions.
I have a question about Q inside. Does it represent the entire charge inside the big sphere?
No, that Q inside is only the charge inside of that Gaussian surface. You see, this is the Gaussian surface which I took. It is smaller than the total volume of charge, right?
All right.
Yeah,
Thank
so
you.
this is the volume inside of the Gaussian surface. So this is a very good question that now it's very important to remember that the flux of the electric field through the Gaussian surface must be equal charge inside of that Gaussian surface. Yeah, any additional questions?
I have a question.
Yes.
So for the volume charge density, did you just make them equal to each other?
Yes. So because I did say on the previous slide as well that the volume charge density is uniform. So in the sphere of charge, the volume charge density is uniform. So the amount of charge per unit volume at any point, whether here or here or here, everywhere within the sphere, the volume charge density is constant, the same.
Okay, so
the charge is uniformly distributed in that sphere.
Yes, so you put them as like a ratio to each other, right?
Yes. So I produced this important equation. This is sort of the trick to solve this question, that the total charge to total volume must be in the same proportion as the charge inside of the Gaussian surface divided by the volume of Gaussian surface.
All right, I got it. Thank you.
Yeah, you're welcome. Any additional questions?
Does it have to be a sphere inside the Gaussian surface? Yeah,
that is a very important question. That the only actually convenient Gaussian surface to solve for electric field on the previous slide, on this slide, right inside, is the spherical Gaussian surface. Remember, so you could select, of course, not spherical Gaussian surface. What if you would select a cube? Well, then remember that now any point on that cube would be at a different distance from the center of the sphere, which means that you would have to expect that electric field on the surface of that cube at every point has different magnitude and different direction relative to the, because area vector would be let's say at this point in this direction, dA, right? Because the area vector must be perpendicular to that Gaussian surface. But the electric field at this point would be radial. So there would be certain angle. So let's say to select the cube would be completely useless to calculate electric field. The Gauss law would be still valid for that Gaussian surface, for that cubic Gaussian surface. Gauss law is always valid. It's an equation. But electric field, or the flux of electric field through the cube would be horribly complicated to calculate, and of course electric field at every point would be different, right, on that cubic surface. So my short answer is the only convenient Gaussian surface to calculate electric field is the spherical surface. And you will see that for all our calculations, the Gaussian surface, which is convenient for our questions, will be either a spherical surface or cylindrical surface, or in some other cases, it might be some other type of closed surfaces. I've explained last time a little bit about this as well. So yeah, so it must be spherical surface to make the flux calculations very easy, like I did on that line, right? Only for spherical surface that calculation of the flux is very easy.
I have one last question.
Okay.
So I don't understand the graph very well. Like
okay. Yeah. So let me try to clarify this a little bit better. So this is the final result. We found that electric field is given by this expression, where Q, capital Q, is the total charge in that sphere, which is given. We know what is the total charge in that sphere. Q is constant. Capital R is the radius of that spherical charge, which is given and constant, right? Given quantity. So the only variable here is that lowercase r, because that lowercase r could be, I could calculate electric field at this point, or maybe at the larger distance. So then I would select a larger spherical surface. So that lowercase r shows you the distance from the center of the sphere. So here I wanted to plot how electric field depends on that lowercase r from the distance, how it decreases or increases with the distance from the center of that spherical charge. So as you see, this electric field is a certain constant. These are all constants. Capital Q, capital R, epsilon 0 are constant. So electric field is equal, let's say, certain constant A, where capital A would be that Q divided by R cubed, 1 over 4 pi epsilon, or everything, times R. So as you see, this is a straight line equation. Where A is the slope. So this is like equation Y is equal M times X from high school, right? So instead of X, we have lowercase r, slope M is capital A, and Y is electric field. So I'm plotting here electric field as a function of lowercase r. And this is a straight line equation, right? When r is equal 0, lowercase r is equal 0, at the center of the sphere, electric field is 0 at the center of the sphere. And then when lowercase r increases, electric field increases in a linear fashion with respect to r. So this is a straight line equation. Until you get when lowercase r is equal to capital R, this is the point. This is the point on somewhere here, let's say, on the surface of the spherical charge. This is where r is equal to capital R, right? So if you substitute for lowercase r, so that would be equal like this. For r equal to capital R, you would have Q times capital R divided by R cubed, right? And here that constant 1 over 4 pi epsilon 0. I'm writing very fast because this R and this R would simplify to R squared, right? So the maximum value of electric field is at this point when lowercase r is equal to capital R. And that's the maximum value of electric field. And outside of the sphere, charge decreases as 1 over r squared, which I did show on the previous slide. Okay, so I show you again so that you understand. See, on this slide, on the previous slide, we have proven that electric field here depends, or like this. You see, it's 1 over r squared.
Okay.
So,
Okay. Yeah, I got that now.
Yeah, thank you very much. So you got it. That's very important. So that hopefully you have no more questions about this.
Sorry, can I ask a question?
Yes, please. Sure.
Sorry. So I'm just wondering about the circle, the Gaussian surface inside the sphere of charge. So that would be already given, right? Because don't we pick the surfaces sometimes?
Yeah, you do, but here you would have to make your own decision what type of surface you select. So that would be sort of part of understanding of how to use Gauss law. That you would definitely have to conclude that the only convenient Gaussian surface is spherical surface.
But from this slide compared to the last slide, what's I know one of them is you're picking the surface to be bigger than the charge.
Yeah, because on the previous slide, sorry, I think that I understand, but on the previous slide, I wanted to calculate electric field outside of the sphere of charge when the lowercase r was bigger, lowercase r was larger than capital R. So then I took Gaussian surface passing through this point, which was distance, large distance. So I took Gaussian surface like this. But on this slide, I'm calculating electric field inside of that sphere of charge, let's say at this point, where lowercase r is now less than capital R. So I took this Gaussian surface. So in both cases, Gaussian surface is spherical, but here that large Gaussian surface is now surrounding entire charge, and here Gaussian surface is enclosing only part of that entire charge.
Are both of those r's given from the beginning?
Yeah. So if I would like to be specific, I could tell you find electric field at distance r equal, let's say, 3 centimeters, right? So then that lowercase r would be given. But I solved the question parametrically. I wanted to get general formula how electric field depends on lowercase r. So I didn't give you specific value, but if this is your question, yes, that lowercase r would be essentially given, right? That is the distance at which you want to calculate electric field.
Okay, thank you.
Yeah, you're welcome. So let us move forward. And so another application of Gauss law, which I would like to use, is to analyze what happens when we charge a metal, a good conductor, a metal. And I remember in physics 1801 that was done, but I would like to now use Gauss law to make few conclusions. What happens if we charge a metal? Because remember, in previous examples, that volume of charge, it was embedded in a plastic, in insulating material, so that the charge inside of that insulating, say, plastic could not move. So charge was stationary. But what if we put some charge on a piece of metal? And as you know, in a metal, there are electrons which are free to move. For example, if you would have metal made of copper, then in copper, every atom of copper is made of about 29 electrons, and only one, that valence one, is free to move from place to place. Right? That is what is that free electron model of metals, that 1 electron per copper is movable, is free to move from place to place. So imagine that I have a piece of any shape of copper. Let's say this is now a piece of copper, like 3-dimensional piece of copper. What do you think happens if I connect and charge that piece of metal, maybe by charging a rod, maybe made of some material, and I attach that charge rod to that piece of copper metal? So this part would be now acquire some negative charge. So again, so let's say if this is that copper metal, and if I put some negative electrons here, right, by touching maybe some, then of course these electrons will not stay here, because electrons want to be far away from each other, because now they repel. So electrons would quickly move to different places, and here that initial large value of electrons would decrease, because these electrons would move to different places, and these electrons would distribute themselves, repelling each other. They would repel each other, and and they would start to move. And after a very short time, maybe about 10 to -9 seconds, these electrons would redistribute themselves in such a way that to maximize distance from each other, right, because they repel, but they would distribute in such a way that electric field inside of that copper metal would be 0. So electron field, after the short time, 10 to -9, electrons would stop moving, they would redistribute themselves, and the electric field inside of the metal would be 0. Now, what happens if I put, let's say, if I charge that copper metal at one point here, maybe with some positive charge, maybe by touching some rubber rod, charge rubber rod to this point of the metal. Then remember, positive charge cannot move. Only electrons can move. So if you put some positive charge on one end of that copper metal, then electrons from here, let's say this electron will move, being attracted by that positive charge. And remember, 1 electron per copper atom is movable, would move here and neutralize some of that positive charge. But this atom, after losing electrons, would become positive. Now, maybe this electron from here would move, being attracted by that positive charge. So this electron would move here and neutralize some of that positive charge. And this atom, after losing electron, would become positive. So again, only electrons would move, and that positive charge, which I initially placed here, would be redistributed by motion of electrons, would be redistributed in such a way that that positive charge would, like in this case, sort of, would distribute themselves, as you will see, on the surface of the metal, and electric field inside of that metal is equal to 0. So electric field, when you charge the metal, after a very short time, electrons move in such a way that that excess charge, that additional charge, whether positive or negative, will be located on the surface of the metal, and inside of the metal, electric field will be 0. Because now, if electric field inside is not equal to 0, then of course, by this equation that F is equal Q times E, if electric field is not equal to 0, then there would be force acting on these electrons. If E is not equal to 0, then electrons will have to continue to move, and they would have to continue to move forever. And when electrons move, they make collisions, so the metal would be heated. So electrons have to stop to move, because otherwise, now the principle of conservation of energy would be violated. The heat would be produced by these collisions, and metal would be heated forever. So electrons have to stop moving after a very short time, and they stop moving only after electric field inside of the metal is equal to 0. And I remember I was explaining this to you now in physics 1801. But so one question is that, yes, electric field inside of the metal must be equal to 0 to stop motion of these electrons. But another question is, where is that excess charge? That excess charge, let's say, if that excess charge is positive, where is it? Is it somewhere within the volume? Or I was telling you that it is on the surface, but that this excess charge will be located on the surface. But to prove that electric field will be located on the surface of the metal, we have to use Gauss law. And here I wanted to prove to you that this excess charge which you put on the metal after a very short time will be located all on the outer surface of the metal. How to prove it using Gauss law? Very easily. Look, if I have a certain volume of metal, no matter what shape, then if electric field inside of that metal must be 0, right? Electric field must be 0, as I have proven to you. Then if I select the Gaussian surface, this dotted line represents certain closed Gaussian surface, which is located as close as possible to the surface of the metal. And because electric field inside of the metal is equal to 0, that means that the flux of electric field, because at every point here, you see, on that surface, electric field is 0. Because that Gaussian surface dotted line is inside of the metal where electric field is 0. So because electric field on the surface is equal to 0, then the flux, now that integral E dot dA, the flux of the electric field must be equal to 0, because electric field is equal to 0. 0 times dA is 0. So so the total flux through that Gaussian surface located close to the surface is 0, which means by Gauss law that flux must be equal to the total charge inside of the Gaussian surface divided by epsilon 0. But because the flux is equal to 0, then the charge inside of the Gaussian surface must be equal to 0 as well. So remember, inside that Gaussian surface, there are many nuclei. Every atom has nucleus, and there are many other electrons around the nucleus, but that positive and negative charge cancel each other. And the net charge inside of the Gaussian surface must be equal to 0 because electric field is 0. If electric field is 0, that means flux is equal to 0. If the flux is equal to 0, the charge inside of the Gaussian surface must be equal to 0, which means that the charge, that excess charge which we put, must be outside of the Gaussian surface. And because Gaussian surface is just beneath the surface of the metal, that extra charge must be on the outer surface of the metal, on the outside surface of the metal, which is represented here. So by using Gauss law, we now were able to prove that this excess charge which you put on the metal after a very short time, maybe 10 to negative 9 seconds, will be located on the outside surface of the metal. And that charge on that outside surface of the metal will be located and distributed in such a way that inside of the metal electric field will be 0. Any questions so far? So far I was proving to you that electric field, when you put the charge on the metal, the electric field inside will be 0 and charge must be located on the outer surface of the metal.
What if the charges are too much for the surface of the metal?
I didn't get your first part of your sentence.
What if the charges are too much for the surface of the metal?
What do you mean too much?
Like too plenty?
No, no matter how much you put it, it will be, all that excess charge which you put on the metal will go to the outside of the surface. Now, if, your question is very good, if that charge outside, which is very large now, let's say, if the charge is very large, that charge on the surface will produce electric field, right? So everywhere outside of that metal will be now electric field because the charge will produce electric field. And if that electric field is large enough, and I will show you in a minute that this electric field will depend on the density of that charge. So if the density of the charge on the surface is very large, which is your question, then the air outside will be ionized. The electric field will be strong enough to rip off electrons from atoms, and this will be ionized, and some sparks will be generated. Some lightning, little lightning will be generated, you know, like, so through that lightning, that charge now will finally be transferred to the outside and to the ground. So that's what happened if the charge will be too large, which was an excellent question, which I wanted to actually explain a little bit on the next slide, because, you know, so for now, I was telling you that when we put some excess charge on the metal, let's say positive charge, then electric field inside of the metal will be 0. That's one important conclusion. That charge, that excess charge will be located on the outer surface of the metal, as you see, and that outside, and that charge will produce electric field. Right, inside of the metal, electric field will be 0, but electric field will be present outside of the metal. And that electric field outside of the metal, direction of that field must be always perpendicular to the surface of the metal, always perpendicular to the surface at any point. Electric field must be perpendicular to the metal. And as I've mentioned, the bigger density of that excess charge, the stronger the electric field. But electric field must be perpendicular to the surface of the metal. Why perpendicular? Well, why perpendicular, I will prove to you in the following way. So imagine that electric field is not perpendicular to electric field. Imagine that electric field is at certain angle to the surface. So if electric field would be at certain angle, then this electric field I could decompose into component of electric field parallel to the surface, and component of the field perpendicular to the surface, right? I can always decompose any vector into two components. And this time I'm decomposing it into component parallel to the surface of the metal and perpendicular to the surface of the metal. And if that component parallel to the surface of the metal is not equal to 0, then this component of the electric field, E parallel, would exert a force on electrons. And that force, as you remember, is equal E times Q. And that component parallel would act on electrons, and electrons would have to move parallel to the surface, would have to move on that surface, as long as this component of electric field is present. So electrons would continue to move on the surface, and when they move, they make collision that creates heat. So that cannot happen. That would be violation of principle of conservation of energy. So the only solution is that in that static equilibrium, after 10 to negative 9 seconds, the electric field must be perpendicular to the metal surface, so that this component parallel is equal to 0. So electric field must be created by that surface charge, must be perpendicular to the metal surface. So this is visualized here as well. You see, no matter what is the shape of that metal, no matter what is the shape, volume of that shape, at any point, electric field is perpendicular to the surface of the metal. So any questions about these important 3 conclusions? That electric field inside is 0, that excess charge is located on the surface of the metal, and the surface charge produces electric field which is perpendicular to the metal surface. Any questions about that?
So I have a question.
Yes.
I didn't quite understand how electric flux was related to this from the previous slide.
Yeah,
Can you
yeah.
explain
Okay,
that
so I know I did it very quickly, so I apologize. But you know, let me let me repeat that argument. So here's the Gauss law. Gauss law tells you something like this: that the flux of electric field through the closed surface dot product dA, right? These are vectors. Must be equal charge inside Qn inside of the Gaussian surface divided by epsilon naught. That's the Gauss law. So now, so what I did was this. I first make conclusion that electric field inside of the metal must be 0, so that electrons do not continue to move inside of the metal. Electric field inside must be 0, because otherwise electrons would continually move and create heat. So electric field must be 0, any place inside of the metal. So if I now take then the Gaussian surface represented by the dotted line, remember this is like a volume of that charge, but the Gaussian surface is just beneath the surface of the metal. So you have a volume of metal, and Gaussian surface is just beneath the surface. But that Gaussian surface is inside of the metal, right? Below the surface. And because electric field inside, at any point inside of the metal must be 0, then the electric field at any point on that Gaussian surface, you see, at this point, or this point on the Gaussian surface, or this point, at any point on that Gaussian surface, that electric field on any point of Gaussian surface is equal to 0. Is that point clear? Could you confirm that you all understand that?
Yeah, I got that.
Yeah.
Thank you.
So if electric field is equal to 0, then 0 times dA is 0. And integral of 0 is equal to 0, which means, because this is the equation, that the total charge inside of my Gaussian surface must be equal to 0, which means that that excess charge must be outside of the Gaussian surface, because charge inside must be equal to 0, which means that the charge lies outside of my Gaussian surface, and my Gaussian surface is just beneath the surface, which means that excess charge must be on the outer surface of that metal, on the outside layer of the surface. So that's the argument which I repeated slowly. Hopefully you got the point.
So would you make 2 surfaces then? Like,
no, I made only one surface. My surface on purpose, I made inside of the metal because I know that inside of the metal electric field is 0.
yeah, but what about if you want to calculate the electric field on those positive charges?
Well, that was not my purpose. My purpose was to make I could, of course, yeah, I understand your question, but my purpose was to show that the charge, that excess charge, must be on the outer surface of the metal, right?
Okay.
So I have proven to you by using Gauss' law that excess charge must be located on the outside surface of the metal.
Okay, yeah.
But of course, I could calculate, if I would like to calculate electric field produced by that charge, which maybe I go to the next slide, right? Because that was your actually question. So if I go to this slide.
Well, I get it. It's not the purpose of what you're teaching.
Yeah,
right
it
now.
was not the purpose. Yeah, but if I could continue your question, but if I would like to calculate the electric field outside, then of course you would have to take the surface, that Gaussian surface, or maybe like this outside, right? But then the flux, to calculate flux to this Gaussian surface would be very complicated because now electric field at different points would be different magnitude, because as you will see later on, that surface charge density, that the density of charge on the outside surface is not constant. As you will see, on the sharp edges, when the curvature is very small, the density of charge is very large. But on these surfaces which are not very sharp, density of charge is smaller. So the charge distribution is not uniform. It's not uniform. I mean, at certain areas, there is a small density of charge, and on some areas is large surface density. So electric field would change from point to point, and it would be very, very difficult to calculate the flux of electric field. Anyway, I think that I did answer your question, so that was great. So now let us use now these conclusions to make some other conclusions. That remember that in previous cases, when I talk about the plane of charge, I always had plane of plastic with embedded charge. But on this slide, I wanted to say, what if we take a plate of metal, not plastic this time, but plate of metal. So this is like the plate of metal in cross section, maybe like rectangular in shape, plate of metal, okay? And here it is, we put some charge on it. We put some excess charge on that plate made of metal. Then, as I was telling you, the charge will be only located on the outside surface, so somewhere here, on that outside surface. And if we treat, these, and if that plate of metal is relatively narrow, so that this width now is very, very small, then most of that charge which I put would be located on this surface, right, on that side surface, and on that surface on the other side of that plate. So that charge would be located, because it's a metal, would be located on that outside surface here and here. So that total charge, let's say Q, which I put on that metal, I call it here Q, would be distributed on both sides of the metal, Right? I ignore again, the width of that metal is so tiny that almost I can ignore it. So the charge will be distributed on this surface and this surface, which means that the surface charge density would be total charge, which I put, divided by 2a, because half of the charge would be on this surface and half on that surface. And I would have like two sheets of charge, very thin sheet of charge. One sheet of charge would be on this surface, and one sheet of charge would be on that surface. And the charge would be uniformly located, because this is like a plane of charge. So charge would have to be uniformly located. So here we have like two sheets of charge. And remember that previously, in previous lectures, we were proven in different ways using Gauss' law or using integration, that if you have just one sheet of charge, let's say positive charge, then electric field produced by one sheet of charge is given by this expression, sigma divided by 2 epsilon naught. But here I have two sheets of charge, one on one side of the metal, the other on the other side of the metal. So the question now arises, what is the total electric field produced by that metal, that plate of metal at point A at point B inside and point C outside on this side. What is that? So of course, we make assumption that that sheet of metal is very large, almost infinitely large, right? So that I can use this equation. Sigma divided by 2 epsilon naught is valid only if the sheet is very, very large. So you see, I have two sheets of positive charge, which means that at point A, each sheet would produce its own electric field. I'm using superposition principle. So this sheet would produce electric field in this direction at point A, away from this positive charge, right, on that sheet. This positive sheet at point A would also produce electric field in the same direction, away from that sheet of charge. Remember, positive charge produces electric field away from positive charge. Now at point B, one sheet, this one on the left-hand side, would produce electric field to the left, away from positive charge, and the other sheet of charge would produce electric field at point B to the left, not to the right, but to the left, because away from this sheet. So you see, inside of that metal, these two sheets would produce electric field in opposite direction. So electric field inside of the metal would be 0 as expected, because it is inside of the metal. But at point C, each sheet would produce electric field again in the same direction, and the total electric field would be now twice as large. So the total electric field outside of that single sheet of metal would be equal sigma by 2 epsilon naught plus sigma by 2 epsilon naught, right? Each sheet would produce the same electric field, which is independent of the distance. The total electric field would be then 1/2 plus 1/2 is 1. And because the charge density is Q divided by 2A, because the total charge was distributed on both sheets, so the total expression for electric field would be Q divided by 2 epsilon naught A, where A is the area of one side of the sheet. So do you have any questions about this example? Hopefully it's all clear. So that was one single sheet, like kind of rectangular sheet of metal. Now on the next slide, I have the example when we have not just one sheet of metal, but two parallel plates of metal, sheets of metal, like in a capacitor from physics 1801. So when you have two very closely spaced sheets of metal, if you charge each sheet, one sheet with positive charge, the other with negative charge. So this is the difference now. One sheet is charged positively, the other negatively. And if these two sheets, very large sheets of metal, are close to each other, relatively close to each other, very close to each other, then what happens is this, that positive charge will attract negative charge, and of course negative charge attracts positive charge. So this time, all that excess charge on that each sheet will be located only on one side of the metal, only on one side of the metal. So there will be no charge on that sheet, on that side. There will be no charge on that side. All that excess charge will be only on this side, you see, because positive charge and negative charge attract one another, and electrons will move in such a way that on both sheets of metal, the charge will be on these opposing sides, this side and this side, nothing on the outside side, because charges attract one another. So the density of charge will be Q, total charge which you put on each sheet, divided by area A, right? Which is area of one side of that sheet. And these two sheets, one positive and negative, will produce electric field in the middle between the sheets in the same direction, because positive charge will produce electric field away from positive, and negative sheet of charge will produce electric field towards the negative. So these two fields will be parallel, you see? That one due to positive, this one to negative will be parallel, and the total field in between the plates will be sigma divided by 2 epsilon naught plus sigma by 2 epsilon naught. The total field will be 1/2 plus 1/2 is 1, sigma by epsilon naught. Sigma is Q over A. So the total field will be Q divided by epsilon 0 A, right? This is the equation which we used in physics 1801 many, many times. I was just telling you that if you take two sheets, very large sheets of metal, if you charge one positively, the other negatively, then electric field between is this much, is given by this expression, and that electric field outside of the sheet is equal to 0. Why outside 0? Because let's say at this point, that positive sheet produces electric field in this direction, away from positive. The negative sheet produces electric field at this point towards the negative in this direction, and these two will cancel. The same on that side. Positive will produce electric field to the right, negative charge will produce electric field towards the negative, to the left, and these two will cancel. So electric field will be only present in between these sheets, like in a capacitor. Any questions about two metal sheets, parallel metal sheets?
Sir, I just have a quick question. I was wondering, how does the space between the two plates affect the electric field?
Yeah, that's a very good question, because these formulas which I have written here are only valid really if the separation between these metal plates is much, much smaller than the size of each plate, which is usually the case. That usually these two sheets will be very close to each other at very short distance. But if the separation is large or comparable to the size of these two sheets, then the electric field is not really uniform.
Uniform, okay.
It's not really uniform, and changes from place to place. But in most applications, you see, engineers do take these two plates very close so that you can use this expression for the electric field due to one sheet. Remember, in the previous lectures, we spent so much time to calculate electric field due to one sheet of charge using integration, using Gauss law. So this expression is, independent of the distance, and that is only true if the sheet is much larger. It's very, very large. Yeah. So your question is very good, but now we will make that approximation that the sheets are always close to each other now at very short distance, which is now much smaller than the size of each plate.
Okay, thank you.
Yeah, excellent. Any additional questions? Now, this example, which I was planning to do, but the time goes so fast, this example, which is related to coaxial cable, I will do in tutorials on Wednesday. So please remember, tutorials on Wednesday are at 9:30, and they are compulsory to attend. Whatever is covered in tutorial will be on the test and exam. And on that test in a week, so remember that the test number 1 will be given on Monday next week. One question definitely, and number of maybe multiple choice questions, true false questions, and one crowd mark question will be related to Gauss law. So make sure that you understand Gauss law and attend tutorial on Wednesday, because during that tutorial on Wednesday, the tutorial will be completely devoted to Gauss law, and many examples will be given how to use Gauss law to calculate electric field. And this example I will do in tutorial as well. The coaxial cable is very, very important. And coaxial cable is just the wire, thin wire surrounded by cylindrical shell. That's what coaxial cable is. So I will do it very thoroughly and properly in tutorial because the time now is too short. In addition, in tutorial, I will explain these 4 slides, which I did not have time to do today, but I will explain this in tutorial, because these are really like problems to solve. So all these examples like this one and of this one will be done in tutorials. Just please make sure that you attend tutorial or watch the recording of the tutorial, because that will be part of the test on Monday next week. But because time is now almost actually lecture is done, so yeah, I will finish that Gauss law in tutorial. And I'm sure that you have questions, but at this point I will stop sharing and stop recording